Saxon Advanced Mathematics, lesson 35. I'm picking up at part B, you guys. We finished part A, and what we learned is that when we're measuring a change in coordinates, and we learned that the way we do that is we take the final position and we subtract the initial position, okay? And we did that just using points on a graph, X's and Y's, and we measured it separately, right? We measured the change in an X and the change in the Y. Now we're gonna take that same concept and we're gonna apply it to a slightly different scenario. John calls this the name of a number. I think that's probably the most random and bizarre title of any of his lessons in any of his books. I have no idea why he calls it that. It makes no sense to me. And we did something like these last year. And it goes like this. What is the number whose graph is 2/3? Sorry, I was looking at the wrong thing. 2/3 of the way from 3 to -7. All right, and John draws a diagram that I think makes no sense. To me, these problems make sense if you just use this nifty little formula. What we're gonna do is we're gonna take the initial number and we're gonna add the fraction. And I'm looking to see, I know sometimes John uses a decimal there. No, this time he just uses a fraction. And then we're gonna multiply that by the final minus the initial. So we're measuring the change in the coordinate and we're taking a fraction of it, right? 2/3 of the way from 3 to 7. So this is our initial, this is our final, and this is our fraction. And now all we have to do is plug in to our fabulous formula and solve. So we're starting at the number 3 and we're adding 2/3 of the distance from -7 to 3. I'm putting buckets here. I could put them here too, right? Final minus initial. Got to keep those minus signs straight. Okay, so that is how we set this up. This formula gives you everything you need to know. All right, John writes a crazy, he does these differently than I do. He makes them, I think, way harder. All right, 3 plus 2/3 times, this is -10, isn't it? So this becomes 3 minus 20/3. I did the multiplication. Now I'm going to change this into an improper fraction that has 3 on the bottom by multiplying it by 3/3. And then 19 minus 20 would be -11/3. So if we're measuring the distance from 3 to -7 and we want to go 2/3 of that distance, the place where we'll end up is -11/3, which is almost -4. Okay? Again, John draws a diagram that I think makes it super confusing. I don't recommend. But this formula does the job. Okay, let's do one more. Let's do 2 more. 35.4. This time what I'm going to do, rather than write down the sentence that's in the book, I'm just going to write down the variables we're looking for. We're looking for the fraction, we're looking for the initial, and we're looking for the final. I'm going to go ahead and write them out because the F's can be confusing, fraction and final. What number is 3/7 of the way from -4 to +9? There are my values. There is my formula. So it's going to be -4 plus 3/7 times 9 minus 4. Okay? And again, we can always call this part of the formula the change in the coordinate. That's what this part represents, is the change in the coordinate. Okay. This then is minus 4 plus, okay, 9 plus 4 is 13. 13 times 3 is 39 over 7. Let's multiply this by 7 over 7 so that they match. So that becomes minus 28 over 7. I'll cross that out. And now I can add, and this time you get 11 over 7. Notice that what we did was we took the same pair of points. No, we didn't. This is a different problem. Never mind. I thought John was having us do it the same way, but never mind. They're different numbers. Okay, we just use the formula. It's easy. One more. Then our third topic. Example 35.5. Find the number. Oh, okay. Let me write down my cues first. Fraction, initial, final. Find the number that is 5/11 of the way from 3 1/8 to minus 3 5/8. Okay, forget about those mixed numbers. I don't want anything to do with them. I'm changing them to improper fractions before we even start. This would be 8 times 3 is 24, plus 1 is 25 over 8. And this is 24 plus 5 is minus 29 over 8. Okay, and then I'm going to put this up here. It's the initial plus the fraction times the final minus the initial. And this is the part we call the change in coordinates. This I copied from the other page. Okay, so our initial is 25 over 8 plus the fraction times minus 29 over 8 minus 25 over 8. The minus signs didn't bother me too much, so I didn't, well, I can just put buckets on there. I should practice what I preach, shouldn't I? Buckets for the win at all times. All right. Well, these denominators have gone a little wonky on us, haven't they? 25 over 8 plus 5 times 11, and then this is minus 54 right? That's 54 over 8. That's getting to be kind of a big number. But we're fine. We're doing it right. Okay. Now, I see that these are both even numbers, and I'm tempted to reduce that, but I can see that these are 8s, and eventually I'm going to have to make these denominators match. So I think that if I make it smaller, I'm just going to have to make it bigger later. So I'm just going to leave it that way. So now we're going to multiply these two. 25 over 8 plus, let's see, 54 times 5. 50 times 5 is 250. 4 times 5 is 20. So this would be 270 to the minus, right? So I'm going to make that a minus over 88. Yeah, and see, that's what I was thinking is now we just multiply this one by 11 over 11, and our denominators will match. So what's 25 times 11? 11s are fun to multiply because you can just write them out. Okay, so that's 275 over 88 minus 270 over 88. So it looks like our final answer is 5 over 88. And that's correct. So this is the number that is 5/11ths of the way from that number to that number. Who knew, right? Okay, so we can use that change in coordinate idea to solve these randomly named name of a number problems that John has cooked up for us. But even more important and valuable is part C, what we call the distance formula. And that is very, very useful when we want to find the distance between 2 points. So, just a second, I want to check and see. I think these are our original points. No, they're not. They're different points. But here we have a little graph. We're taking the number, or the point, minus 3, 4, and this one is 4, 2. And we want to find the distance from here to there. We don't care about the direction. We just want to know the distance from there to there. So the easiest way to do this is to rely on our friend Pythagoras and calculate this as the hypotenuse of this cute little right triangle that we just made. By the way, it used to drive me crazy when I was first learning this because I couldn't understand, how come you don't draw the triangle like this? And here's the answer. You can draw the triangle like that and do this. It'll work exactly the same way. The convention is to go down and to the right. This seems kind of upside down to most mathematicians, but it will still work. You can still do it that way if your brain sees it that way, which mine did. Okay, so what we're gonna do is we're gonna remember how this works. And we're gonna call this, let's just call it C, that's fine. It's the hypotenuse. We know that the Pythagorean tells us a squared plus b squared equals c squared, right? And we know that we can rearrange this. Well, we can just take the square root of both sides and put the c on this side. C equals the square root of a squared plus b squared, right? That is just a little bit of algebra on our Pythagorean theorem. Now, let's look at what A represents and what B represents. A represents the change in the y coordinate. And B represents the change in the x coordinate, right? Let me just put these in to help you remember, right? A is the change in the up and down, and B is the change in the side to side, so x and y. So this is the change in the x coordinate. Now, this is helpful because in this example, and many of the examples we have, we don't know the length of these sides to plug in as A and B, but we do have the 2 points. So what we can do is rewrite this equation using what we've learned about the change in coordinates to substitute for what A is and what B is. A is the change in the y coordinates, B is the change in the x coordinates. Looks like a V, doesn't it? All right, so I'm gonna go through, this is our first version of the Pythagorean theorem. Then we simplified it, and now we're gonna take this information and write it in a third form. And we're gonna call this x1 and y1, and we'll call this x2 and y2. So, what we're gonna do is we're gonna write the change in the y coordinate as y2 minus y1, and then we need to square it because that's Pythagorean. So there's the change in the y coordinate. It gives us a. And then we have to add to that the change in the x coordinate, which is x2 minus x1. And again, that squared. And then the last thing that we're going to do is we're going to change this letter, and we're just going to make it d for distance. So this is something very useful and memorizable called the distance formula. And this you need to write in your book. Somewhere important. Oh, I should be puffy clouding this, not drawing a square around it. Okay. So pause me right now and write this in the front of your books. It's called the distance formula. Pause me and then come back when you're done. Okay, one thing I wanted to point out about this that John points out really carefully, because we're squaring these changes in coordinate, we could measure them in either direction. We could measure from here to here, which is what we did, or we could measure it from here to here. We remember that we would get the same number with the opposite sign, but we're squaring it. So once you square it, it's always going to end up positive, right? So it doesn't matter anymore. So we don't have to think about the direction in these because either way, we can measure it either way, get a positive or a negative value, and then once we square it, we'll be positive. The other thing we could do, because this is addition, is we could do the x's first and then the y's if we wanted. It doesn't matter because we're adding. In an addition, order doesn't matter. There, I was saying it right. So there are actually 4 forms of the distance equation that I'm going to show you in your book. This, where is it? This is the one that I like. No, that's not it. John does not have the version the way I like it, but all of these will work. There are many correct forms of the distance formula. 4 of these correct forms are. So as long as you're subtracting one x from the other and one y from the other in the same order, well, it doesn't even matter if it's the same order. These are mixed up. And then you're squaring each of those and adding them together, the order doesn't matter so much. The reason I really like this version of it is because we already know a formula that looks kind of like this. We have our slope formula, right? This is slope formula that we learned, I don't know, last year or the year before. And this is y2 over y1, or y2 minus y1 over x2. That matches to the this version of the distance formula the most closely. So I like to memorize this one because it uses a piece of your brain's memory that you've already got locked down, hopefully. So let's recognize that there are many different forms of the distance formula. The fact that we're squaring takes away any value, any importance to this original sign, and the fact that we're adding means we can mix and match them. So that's the distance formula. How do we use it? We have one more problem. It is problem 35.6. And it says use the distance formula to write an expression that gives the distance between the point 4 minus 2 and some other point x, y. Okay, so what John's saying is I'm not going to give you numbers and let you calculate. I'm going to give you a mashup, and you have to create like a semi-abstract expression. All right, we can do that. Let's start by writing down that formula. y2 minus y1 squared plus x2 minus x1 squared. This is what's on top of the slope formula. That's what's on the bottom of the slope formula. I square it because Pythagoras wants it that way. I take the square root of the whole mess. It's an ugly looking formula, isn't it? Yikes. Okay, so then what I'm going to do is I'm going to name these guys x1, y1, x2, and y2. That will tell me which blank to put them in. So the distance that John wants us to find, and I'm going to make it a little bit bigger, y2, it's going to be minus 2, so it's going to be plus 2. And then x2 is x minus 4. And that is the correct answer. And I just want to show you John gives us two versions of the answer. Let me put this up here because it's down at the bottom of this page. John writes the answer like this: 4 minus x quantity squared minus 2 minus y. That doesn't look very much like our answer, does it? This one looks a whole lot closer. X minus 4 squared, y plus 2 quantity squared added. So ours looks a whole lot like this, and then it's just in the opposite order, right? The quantity values are the same. They're just listed in a different order. Although the entries appear to be different when the terms in the radicands, John, they're pig houses, okay, are squared, the radicands will be identical, okay? And that is what's important, is that the squaring takes away the negative signs, okay? So both of those are correct. That may occasionally cause you a little bit of drama if your answer is in a different shape than John's answer for these problems. But usually we will take it all the way down to an actual number and you'll get the right answer no matter which order you use. Okay, that is lesson 35. I hope you enjoyed our chat about changing coordinates. And next time we're gonna go back to some trig, and remember the boat in the river problems? We're gonna do those again. I cannot wait, personally. Okay, bye.